We tried some easy fixes. In the first part of this series, we looked at the galaxy rotation problem. Stars at the outer edges are moving too fast based on the mass we can see. In part 2, we explored dark matter, the idea that there may be additional unseen mass providing the extra gravitational pull needed to hold galaxies together. In part 3, we looked at a different approach. Instead of adding mass, we can modify how gravity behaves at large distances using ideas like MOND. Each of these approaches is a relatively simple fix, different ways of extending our gravity-based models to match what we observe when the current picture appears to be incomplete. Spiral structure adds another layer. Galaxies are not just rotating collections of stars. They also show large-scale structure, especially spiral arms that persist over long periods of time. There's a problem here. Even though stars at different distances move at similar speeds, those closer to the center complete their orbits faster. If spiral arms were made of the same stars moving together, they should stretch, wind up, and eventually disappear. However, that's not what we observe. The arms remain stable. So to explain this, scientists use ideas like density waves, where stars and gas move through regions of higher density that form persistent patterns. So now we're not just explaining motion. Our models also need to explain how these large-scale patterns form and persist. Galaxies have even more features. When we look at galaxies in more detail, we see that they are not simple systems. In addition to rotation and spiral arms, many galaxies have central bars, regions of intense star formation, and large-scale flows of gas moving through the system. We also see different types of galaxies, some with 2 clear spiral arms, some with many arms, and others with very different structures altogether. These are not random features. They are stable, repeating patterns that suggest something deeper is organizing the system. Simple models don't scale cleanly. The models we use for gravity work extremely well in systems like the solar system, but they are still models, simplified descriptions of how we think nature behaves. As we move to much larger systems, like galaxies, we begin to see emergent features, including large-scale structure, persistent patterns, and stable configurations that aren't fully explained by simply extending those models. In complex systems, these kinds of patterns often come from interactions, constraints, and feedback, not just from a single rule applied at larger scale. So instead of continuing to adjust our existing models, we may need to step back and ask a more basic question. Are we using the right framework to describe the system at all? Are we missing something more fundamental? At this point, we have multiple ideas that explain different parts of the system. Dark matter helps with rotation. Modified gravity adjusts the force. Density waves describe the structure. But can we simply combine a small set of simple models and fully capture the behavior of a complex system? It may be worth asking a different kind of question. Are we trying to force a complex system into overly simple models, and in doing so, overlooking deeper structure that might better explain what we can observe? A different way to think about the problem. If galaxies behave like complex systems, then we may need a different way to model them, one that allows for phase changes, local variations, environmental conditions, and other system-level effects. Let's go back to the basics and re-examine some of the core components of our models, looking at them from an information systems perspective. We can look at the broader properties of space, the signals that move through it, and the matter that responds to those signals, and begin to explore how these pieces might interact. In the next few videos, we'll take that approach and examine each of these pieces to see what new insights might emerge.